Welcome everyone, I am Manuel from the University of Calabria, and in this video I'm going to talk about our research project which focused on the modeling, assessment and evolution of surface performance of microsurfacing. The main functional characteristics of pavement such as friction, noise and drainage of rainwater are strictly related to the surface texture, which can be identified as a combination of three different domains: micro, macro and megatexture. Due to this importance, it will be appropriate that road engineers consider the surface texture already at the design stage. And in fact, several prediction models can be found in literature, but very few studies deal with modeling macrotexture for surface maintenance treatments. Among these latter, microsurfacing is becoming very popular. It consists of a mixture of aggregates, polymer-modified emulsion, mineral filler, and water that properly proportioned are spread over a prepared surface with a very low thickness. It provides a regular and even surface with a remarkable improvement in skid resistance, and it promotes road safety, cost-effectiveness, and environmental sustainability. Several studies achieved accurate mix design, mainly focusing on mechanical performance, but a comprehensive knowledge on microsurfacing performance is needed. Therefore, the present research proposes a methodological approach that consists in the development of a predictive model to forecast the expected mean texture depth, MTD, from a given mix composition, a study on mix design optimization and evolution of the surface performance, and design and implementation of a prototype for paving microsurfacing indoor. So let's move to the first task. The analysis of literature provides 65 microsurfacing applications, gathering information about the aggregate gradation, the bitumen emulsion and mineral filler percentage, and the macrotexture achieved. Then a macrotexture model was set up in terms of one main equation based on a volumetric approach by using a multiple linear regression. Now, imagine a unit volume of microsurfacing spread over the surface, and this volume is the sum of different components: the aggregates, the bitumen, and cement. And the volume occupied by these components differ from a control volume of a quantity that is actually the corresponding MTD, considering a unit surface area. The control volume, and therefore the control thickness of the layer, depends upon the maximum aggregate size in the mixture. The other volumes are function of the application rates, the grading curve, the bulk-specific density of the aggregates, bitumen and cement, and the percentage of bitumen and cement. The use of regression coefficient completes the model. Highlighted in gray color is the surface texture of the underneath surface, that probably could influence the surface texture of the new layer. However, only few data provide information about the initial MTD, and therefore it would be meaningless to use for training the model. Here is an example of data from literature where the MTD before the application range from 0.5 to 0.65. Statistical performance of the model was recorded by using a k-fold cross-validation technique to confirm the good generalization and the basic assumption behind the modeling phase. Model was applied then to the whole dataset, and the accuracy was assessed by means of statistical metrics. Given the heterogeneity of data collected, the model shows excellent prediction performance with an R-squared of 0.9. Here I provide an example of how the model works. Among the data, three mixtures with the different grading curve, G1, a dense curve, a middle fuse, G2, and an open curve, G3, with same percentage of bitumen and cement. The more the grading curve is open, the more the estimated macrotexture. Same can be said with the residual binder content, fixing the particle size distribution and the cement. Anyway, the influence of the bitumen is lower than a change in the grading curve. Let's move to the second task. A 3-month period of research was conducted at the University of Minho in Portugal. Here we focused on manufacturing 3 different microsurfacing mixtures, a basalt 08, basalt 06 and a granite 08. The gradation are provided from the RILEM Technical Committee, which deals with cold bitumen emulsion materials. Then, by means of a laboratory-scale traffic simulator, we focused on the evolution of the microsurfacing surface performance. This period abroad was really important as it represents the first experimental application for validating the model. I will not focus on the mixed design procedure and the results obtained. Here are just some pictures about the tests carried out according to the EN standard series. Once the optimization phase was completed, the mixture with this final composition were laid by hand above the track, as I show you here in the video. We use some guide to maintain the desired thickness. In this slide, I'm going to show you how the model works with the experimental data. The underneath surface was characterized by an high MTD in comparison to the values found in literature. The model detected the difference between the grading curve, but underestimated the MTD. By introducing the MTD of the underneath surface, the regression coefficient is higher than the one found for the data I showed you previously, but the values settle in the high part of the model and inside the confidence interval. For studying the evolution of the performance, the experimental plan is composed by 6 different times of conditioning at different number of tire passes. At each step, measure of British pendulum number, BPN, sand patch, thready laser and circular laser were collected. Here I show you some raw data about the evolution of the skid resistance in terms of BPN and MTD, whereas the graphs below, the results are normalized and in percentage in respect to the initial phase to time t0. Finally, the last part of this presentation deals with the design and implementation of the U-Micropaver, a laboratory-scale device for paving microsurfacing indoor. The realization phase starts from 3 main concepts. First of all, obtaining an even surface that has to be as close as possible to the reality, and we ensure this by having control on the discharge volumes, the adaptability to the paving surface, and the movement along a direction with a certain speed. Here I show you a brief video of the from the software used for modeling the prototype. The construction of the prototype is financed by a PRIM project and was also presented during a meeting of the RILEM Technical Committee that I said before. Here are some photos regarding the assembly phase. At present, we are in an important phase that deals with the optimization of the speed and the dosage parameters. Also we finally submitted the patent at the Italian Patent Office. So, to conclude, the model works adequately in predicting the MTD. The first experimental value for the validation are quite representative, less than the influence of the underneath surface. The research at the University of Minho allowed to collect data with the purpose of defining a possible decay model for microsurfacing surface performance. And given some limitation of the model, additional laboratory tests are required, and therefore the implementation of the prototype will allow to collect a larger set of data. Moreover, the possibility of laying microsurfacing on slabs made with different mixture will allow us to understand how the underneath surface could affect the new layer. Finally, the implementation of this device will allow for a fast paving method, obtaining a small laboratory scale test field for the study of the other surface performance, such as noise absorption, and drainability. Thanks for watching.